Welcome to the Mood Ring Part 1 Exploring Color. Let's do Challenge 3. First, let's navigate to Challenge 3 by pressing the Control touchpad click up, scroll down, find Challenge 3 page, and center select to bring it forward. In this challenge, we'll be using the color mixing simulation and try to discover the red, green, and blue values that produce white. We will then write a program that displays white, and we'll try to make two darker shades of white. Darker shades of white are termed gray. And then we'll also use a sleep of 2 seconds among those different grays, as we did in the previous challenge 2 with the secondary colors. So we're familiar with this program. We're also familiar with the simulation. Let's get straight to it and go to the simulation by, again, Control touchpad click up, scroll up to the simulation, highlight, and select to bring it forward. We recall to move the box around. I Control click it and drag it, and I see my familiar magenta secondary color formed from red and blue. And I'll also grab my green and drag it over, and here I see quite a lot of mixing going on. I see the secondary color from red and green and the secondary color cyan from blue and green. But interestingly, in the center, where all three colors overlap, I see white. So white must be the sum of all three colors falling on our eye at one time. So with additive color, the three colors together make white. Now, we will recall from the Weber-Fechner law that we learned about in a previous video that it takes about 10 times more power to double the stimulus to one of our senses. Or another way of looking at that is we must cut the power down by a factor of 10 or 1/10 in order to get half the stimulus. So if we make white light, in order to make a darker shade or grayer, we'll have to knock those values down by about a factor of 10. All right, well, let's give this a try. Let's move to our Python editor. But before we do that, I would like to pause here and give you an opportunity to explore more with the color simulation and making white. And when you're ready, navigate to the Python editor for Challenge 3 and start the video back up. Let's get started with Challenge 3 coding. Navigate to the next page by Control touchpad click to the right. Remember, we always have to add the TI Hub module. I'll add that from the Hub menu. Now I'm ready to get started coding. I recall from the simulation that to make white light, I need to use the sum of all three colors in my color.rgb command. So let's do that now. I'll go to the TI Hub, and then I'll go to the built-in devices, color, and RGB. Here I'll put in my three values for maximum color on all three channels, and I'll click once to get out of the parenthesis and enter to go to the next line. Now I'm ready to run this program. I'll use the shortcut combination of Control and R. That takes me to the next page as a shell, and it turns on the Innovator Hub's color LED to white. Let's try to make it grayer now. Remember the Fechner-Weber law that said to make this intensity over here on the right about half as bright, kind of like when you put your headlights from bright to dim on your car. I need to change these values by about a power of 10. In other words, divide them by about 10. So I'll just kind of round down, dividing by 10 to 25. And I'll do that for all three values. And I'll try running this again. Sure enough, it is dimmer, a little bit more toward the gray. Recall that when it is turned off with the values of 0, 0, 0, the absence of light in emitted color theory is 0, 0, 0. So when you see black on a TV or a computer monitor, it's because those color LEDs are not turned on at all. They're turned off, 0, 0, 0. I'm going to give you time now to write this whole program on your own. So you're going to want to add the three color statements along with the sleep to give time in between. I'll give you a moment to write that program, so pause your video now, and when you're finished, resume the video and I'll show you how I work the problem. Now that you've had a chance to code Challenge 3, let's take a look at a solution. I started by importing TI Hub, as we always do. Then I included the color.rgb method using the three values that we determined in the simulation. When I add red, green, and blue additively, I use 255, 255, 255. Then I use the sleep command with 2 as the argument to pause the running of the program for 2 seconds so I can see the color on the LED. Then I reduce the RGB values to 25, 25, 25. I did this in accordance with Fechner's law. As we learned about before, you need to reduce the power value by about 10 to cut the intensity of the light in half. Then I put in another sleep for 2 seconds, and again I illuminated the color LED using the values 2, 2, 2, again a reduction of about 10. So let's see how this plays. I'm going to press Control and R and watch the hub on the right. There's the bright white, the dim white, and the very soft white. Well, I hope you had success coding your 3 white intensities. If not, take this moment to try to correct your code and try to get it working. Having patience with yourself and sticking to it are important skills in coding. Let's review the big concepts from Challenge 2 and Challenge 3. Red, green, and blue are the primary colors of emitted light. Remember, that's additive color, not subtractive. Cyan, yellow, and magenta are the secondary colors created by mixing two of the primary colors. White light is the presence of the three primary colors. 255, 255, 255 is brighter white light than 25, 25, 25. And black is the absence of all colors. Now that we've finished Challenge 3, let's explore more about white light. It turns out that white light has different shades. Have you ever wondered why a light in a candle has a yellow color? Where does that yellow color come from? Now, a flame is a very complicated thing to analyze, and we're going to do a simple analysis, but we're going to focus primarily on that yellow color. That yellow color comes from the hot carbon particles in the flame called soot. Those hot particles actually give off light. Let's learn about how hot objects give off light. To do this, I'm going to look at another simulation that is not included in the document that you have. This simulation shows a horseshoe being held by a farrier's tongue. A farrier is a person who makes shoes for horses, and the tongue is how they hold the horseshoe in the forge, which is a very hot fire that gets the shoe malleable so the farrier can fit it to the horse. So this is a horseshoe, and right now it's at 0 Kelvin temperature. Kelvin is a temperature scale like centigrade and Fahrenheit. One difference, though, is that 0 Kelvin is said to be absolute cold temperature. In other words, 0 is as cold as it can be when it's in Kelvin. After all, 0 degrees centigrade is the temperature of ice, and on a hot Texas day, I can tolerate that quite well. And 0 degrees Fahrenheit, well, that's more chilly than 0 centigrade, but it's still not bad. If you're going skiing, it feels pretty good about 0. But 0 Kelvin, you could not survive that. That temperature is so cold that all of the particles that make up the horseshoe don't even move. Now, when those particles do move as they warm up, they begin to give off something called radiation. Radiation is a kind of energy that is emitted in something called the electromagnetic spectrum. And so, as I warm this up, notice what happens to the horseshoe. So let's say I pulled it out of the farrier's forge and it was at 250 degrees Kelvin. Well, that's a little cooler than room temperature, so that's not very warm, but it gives off infrared light. The particles in our bodies right now actually give off light. But infrared light is light that our eyes cannot see. So we cannot see the light that our bodies emit. However, there are infrared lights that are used in, say, remote controls that give off light that, although we cannot see it, there are optical devices that can see it. Like, for example, night vision goggles can see the light that's given off by our bodies just due to the temperature of our body being at about 270 or so Kelvin. And so actually our bodies are a little warmer than that. But as we go up in temperature, it still gives off infrared light, 500 Kelvin. 500 Kelvin is about the boiling temperature of water or so, a little hotter than that. As it goes up higher, though, all of a sudden it starts to give off visible light. You've probably seen this before. If, like, say, a poker is in a fire, you might find that wrought iron poker gets red hot. You've heard of people say red hot. Well, here we can see the horseshoe is getting red hot. as the temperature goes up still higher, notice that the color gets a little more cherry red. Again, as it gets hotter, the color changes to, again, a little more cherry red and perhaps a little orange. And all of a sudden we start to see a little bit of orange. As it gets hotter, maybe some orange and yellow. And there's full yellow at 2000 Kelvin. And as it starts to get hotter, the color of the horseshoe changes. Now, this is, nobody's shining a light bulb on this. This is actually light that's being made by the iron atoms inside of that horseshoe. As it gets hotter still, the color becomes a different color. It becomes more yellow. And now we're starting to see a whole mixture of colors, and it starts to be white. In fact, white hot is an extremely hot, high temperature. And we can actually see at the tips here, it's starting to turn almost a light blue. Ultraviolet light starts to be given off at higher temperatures. So it turns out that color can also be described as the temperature of what's said to be a black body. A black body, again, is when this thing is very, very cool. At zero, absolute zero, it gives off no light at all. That's why it's black. Black is giving off no light. So this is a black body because it's at 0 Kelvin. It's not giving off any radiation. And as it warms up, it gives off different colors of radiation. And so we're going to learn more about radiation in the next activity, but this is kind of getting us started to think about it. So we can describe light color not only by its RGB value, but also by temperature. Now, you can play with this a little bit on your calculator. If you take the 255, 255, 255 and change it a little bit, maybe try to reduce the red and the green to say 220 and 230 and leave the blue 255, you'll actually have a little bluer white, which is called a cool white. Similarly, if you left it more red, 255, 230, 230, in other words, reduce the blue and the green and keep the red full on, you'll have a redder white light, which is sometimes called a warm white light. And so white is not always white. And so here we can learn a little bit about black body radiation, and we can see that the temperature of the object makes the color. So again, why is my flame yellow? Well, you can see that that is a temperature that corresponds, that yellow kind of corresponds to about, right about in here someplace. That yellow at the end there is kind of about the temperature of that flame. And that's because there's carbon in the flame that is left over from the burning of the butane, and that carbon is getting extremely hot. And when it gets really hot, around 2750 or so Kelvin, it begins to give off light, and it gives off that yellow colored light. Now, this is also used in light bulbs. So a light bulb, at least an incandescent light bulb, is made by taking a piece of wire. In the case of modern light bulbs, it's usually tungsten steel. And that tungsten is a wire that can get very, very hot. The melting point of tungsten is somewhere around 3700 degrees Kelvin. And so if you pass electricity through that wire, it'll get really hot, kind of like a toaster. In fact, I'm sure you've seen a toaster. When you press it down, you can see the wires, and they're getting red and yellow inside as it gets hotter and hotter. Well, if it gets up really hot, it'll start to glow white. And so the white that we see from an incandescent light bulb that has a tungsten filament is really black body radiation of the wire that's up around 2700 degrees Kelvin. And so light bulbs often have colors associated with them. And so here we see a fluorescent light bulb. This is a different technology from the incandescent light bulb. It makes light in a different way. But you can see it has a little bit more of a blue color. It's a cooler white. Now, interestingly, we use the word cooler to represent the blue color. We think of blue as being cool, but actually it's a hotter temperature to get it that temp color. Similarly, this warmer white is actually a cooler temperature. So it's kind of one of those strange things of names. But this cooler temperature from 5500 Kelvin is a color of white light. Similarly, the 3500 Kelvin is a different color. This one's kind of intermediate between the redder 2700K and the bluer 5500K. We kind of have an intermediate here of about 3500K. So color temperatures are very important, particularly in photography. Photography is very interested in color temperatures. A professional photographer will buy studio lamps that have a certain temperature, and then they'll match that with the kind of camera that they're using. The sensors and cameras are sensitive to certain colors, and all of this is called white balance. In other words, you want the color of the light in the studio and the sensitivity of the sensor to be matched. So if you have a 3500 Kelvin studio light, you want to have your camera set to about 3500 Kelvin in order for the white to look white. Let me show you what I mean here. Here is, you're looking at my video camera right now. You can see me waving, hello. And notice that the background looks fairly white. Well, you know, there's a control on here, right here. It's called white balance. And check it out. White balance is given in Kelvin. That's what we were just talking about. So if I take this and I drag it, it changes the sensitivity. Now, remember that a cooler black body radiator is red, more red, and yet my white is turning blue. That's because it's balancing out it's compensating. And so the blue compensates the extra red to try to bring it back into white balance. Similarly, when I come over this way, the higher temperatures turn warmer colored, more red and orange. But again, that's because we're trying to cancel out that brighter blue white light that comes from 10,000 Kelvin lighting. So I hope that you've learned something about white balance and about color temperature. And the next time that you're in the store, you might look in the light bulb section and see what the temperature rating of the light bulb is. That's the white balance. And then someday, when you are in physics, you'll learn about black body radiation, and you'll remember how it relates to the color and your RGB programming of the TI Innovators Hub. So I hope you enjoyed exploring more about color.